So now that we looked at like what a task is, how they sort of roughly abstractly work, how we create them in FreeRTOS, and then there's like the scheduler that controls their execution. We sort of now need to get into the more like complex sort of area of the whole problem, in that you can imagine that you have sort of multiple tasks running concurrently, or literally if you have multiple cores at the exact same time on your system, and they need to both access like these resources, or sort of like essentially the same memory addresses, right? So this is the thing, again, because we're using C or on a hardware device, variables and resources, meaning whatever it is some sort of memory location. But if two sort of things I want to access at the same time, you need to have sort of safeguards in place that you don't run into like errors, because if one like really basic example, which we'll cover in more details later, is that if one task is writing to a memory location and one task is reading it, so weird things can happen and you get data corruption, and this can like lead to unexpected behavior, undesirable behavior, or really just, you know, in a system crash in some cases. So we need to talk about how we do thread-safe programming, because we've now sort of learned that we can create multiple tasks, multiple threads, and run them using a scheduler. So we learn how to address these problems. And so the problem is, as I quickly mentioned, that they have these shared resources. And so we need to find out a way that these resources can be shared between tasks, that we respect the system's concurrency capabilities, right? And so this concurrent access is not like, there are hardware things that are used to make it possible, but a large portion of it is from like libraries, but most importantly, it's done by the user. So there are programming languages and libraries out there in the world that make this whole sort of this process safer, meaning that the user can't make as many errors. But for instance, when we're dealing with FreeRTOS, the guarantee, or there is no guarantee that what you're doing is safe. This sort of lands with the user or the programmer to write code that respects thread-safe programming like principles, right? And so this is the example, as we can see in this last point. But also, for instance, what we can call here as a race condition is that a race condition, for example, is then that things need to be done in a certain order. And so if you're doing sort of simultaneous things, like on two separate cores, you're not guaranteeing the order of things, and therefore you can land in what we call a race condition, and this can lead to undesirable, unexpected, or system crashes, like undesirable behavior, right? So then an example of when we would get, for instance, this last one here, this undefined behavior or a corrupt data, like a perfect example, where then let's say we have just like even on a single core, so it doesn't, I don't think the core itself here is a problem, but we have two tasks, task A and task B, and so task A wants to increment a variable, meaning it wants to go into memory and take a variable and increment it. And so a priority task B preempts task A and also wants to increment the same variable. So this means that the same memory location, task B wants to increment. Now, the thing about how variables in memory are actually incremented is that they use the, like you have obviously assembly instructions and the registers that are used to essentially load the value we want from memory, move, like we sort of want to do this, we're using this moving of a constant and this ORing to increment, and then we store the new value back, right? So we're using these general purpose registers, which we mentioned in the context, which are used to, like they're required with the context of a task. So essentially we load the value from memory when we want to increment, we increment it, and we write it back. And this is done using the registers, the system's registers, right? And so this is what's called a read, modify, write operation, okay? And so the problem is in that this increment is actually not atomic, meaning it takes more than one instruction to complete. We need 4 instructions here to increment the value of a variable in memory. An atomic instruction is when the incrementation of a memory location is done in one instruction. meaning it can't be interrupted because it takes one clock cycle. So you can't stop halfway through a clock cycle and do something else. During a clock cycle, sort of the behavior of a system during one clock cycle is sort of like, I guess, known. You can't interrupt the system halfway through a clock cycle. And so this is one thing that's important, this non-atomic operation, right? Now, the problem is that, for instance, we think that task A is wanting to increment the variable. So if we go back to our scenario, task A wants to increment the variable, and task B also wants to increment the variable. And so we use this read, modify, write sort of sequence. And so task A is firstly going to read the variable. So it's taking, at its point in time when it's running, which is running first, it takes the value into its registers. It is then preempted by task B. So the task A's context is saved, including its registers. So where this value has been saved into its registers, this is saved. So task A essentially has the value of the value of the variable in memory from back in time. Task B then reads the variable again from memory into its registers, increments it, and writes it back. So it performs the operation in its entirety and writes it back into memory. It's then finished, and because it's finished, it goes to a block state and it gives up the CPU to task A again. So task A keeps running, its registers are reloaded from its stack and its context swap. But you can imagine now that the value in the register from task A is the value that this variable in memory had before task B preempted it. Task B has updated this variable's value in memory, but task A has the old copy of its value, so a corrupt copy. All right? And this is what data corruption is when you have a value that's not valid. It's not what it should be. So then task A is going to increment the value it had already saved into its registers and write this back into memory. Now, for instance, if we have these two tasks doing an increment, what we want to do is we want to get if we had an initial value of 1, we want to get to a value of 3. But task A is going to take the value of 1 into its registers. It'll get preempted. Task B will take the value of 1 into its registers, increment it, and write value of 2 back into memory. It will then block and give up control back to task A, which has 1 in its registers. It will increment it to 2 and write it back, and so we have the value 2 in memory at the end. But we should have the value 3 because we're doing 2 increments. We're going from 1 to 2 to 3, but we don't. We have corrupt memory, and so this is not desirable behavior. And so this is the problem with resource sharing and how we need to make sure that two tasks are handling or sharing this variable properly so that we don't have problems like this, right? So we can find similar problems to this between, for instance, like input outputs, meaning that we sort of do the exact same thing. This variable could just be an input stream. We need to make sure that we're not using or not creating corrupt data or using old data. Non-atomic access to variables. So this is exactly what we were talking about now. And for instance, non-reentrant functions that, for instance, use global variables. So you can imagine two tasks are using a global variable. If they use it at the exact same time, then we also have two tasks accessing the same data at the same time, and this is a problem, right? So the solution to the problem is called locking. Now, locking itself comes in lots of different forms, but like the word locking in computer science stands for this sort of creating some sort of control that prevents this simultaneous access, right? And so this is what, I've written this here. And so the whole idea of, I think I was mentioning it in the previous lecture, is the idea is that you have this lock that you need to obtain before you do something, and you give it back. So it's like when you're sitting in a circle and only one person can talk and you have a ball that you throw around. The person that's talking has first gotten the ball, they then talk, and then they get rid of the ball. So they obtain the lock, they do their thing, and then they get rid of the lock, right? And this actual lock is implemented using hardware, and these hardware using atomic instructions. So these are instructions that happen in one clock cycle. So if you take the lock, you're guaranteed that it's going to happen in one clock cycle, and therefore no one else is going to take it at the same time, right? And so this is how we use atomic instructions to create locks. And so this is this analogy, and so this is what we're going to look at, like how do we achieve this then There's a few different ways that you can do this using the POSIX standard, using just general computer science terminology, but then also using FreeRTOS. And so essentially the most basic form of a lock is called a semaphore. And so like a semaphore is really at its core a value that's either 0 or 1, right? It's it's either 0 meaning it's like there, or it's 1 that it's been taken. And this is this sort of atomic increment, right? Is that you can use a value in memory, you atomically increment it to say I've taken the memory, taken the lock, and then you atomically decrement it to put it back to 0 to say I've given it back, right? And so they don't protect against priority inheritance, we'll get to soon. And for instance, they can obviously then not have a value below 0. This will just lead to data problems because the underflow. And so then, for instance, there are sort of semaphores where you're allowed to increment the value above 1. And so these, for instance, are called counting semaphores. And this can be really useful for if you want to sort of count in a locked thread safe way the amount of events that have happened, such as like the amount of network packets that you've received that need processing. So as you receive them, you increment it, and as you process them, you decrement them. So you can sort of keep track of how much is there to be done. But then you're also sort of making sure that you're not two threads that are receiving are not doubly, or not doing this whole read, modify, write problem where you actually lose track of the amount of packets you actually have to process. And by using a counting semaphore, you guarantee that it's incremented the correct amount of times, so that your sort of history or your count is never corrupted, right? And so if it's not able to count, and so if the value is capped at 1, we call this a binary semaphore, meaning that it can only ever be taken once and returned then. It can't be taken multiple times. This would be a counting semaphore, right? So the FreeRTOS API for it is quite simple. We have the sort of creation function to create it. We have a handle, which we have here. The semaphore is where we would place in a handle, similar like when we're using a task. We have a task handle to reference the task. We have a semaphore handle to reference the semaphore that we're talking about. You have to initialize the handle by essentially invoking the create binary function. You then take it and you give it. And so we have a block time here. And so what the block time here is talking about is it's saying, okay, this task wants to try and take this lock. It wants to get control of it. If the lock isn't available, should it wait? Meaning, so like usually the block time is either no, it shouldn't wait, it should keep going, or yes, it should wait forever. Sometimes you might, for some weird application, have some time between, but it's generally either, okay, I'm going to wait forever until it gets free and then take it and do my thing, or I'm just going to forget about it and do something else, right? But that's what the block time talks about here. I've sort of described it here. So then you take it and you give it. So obviously when you take it, you have to give it back. Now I'll talk about slightly how FreeRTOS's implementation of a semaphore is slightly different to the classic implementation. Because the classic implementation is that you take the ball, like in this talking circle, you do your thing and you give it back, right? So FreeRTOS has slightly modified this, and we'll get to it in a little bit. But now then we also have, for instance, the exact same thing to create counting, and so we have the max count and the initial count. So these are just the initial parameters. Same deal as the create binary. Obviously, it doesn't have a count or initial count because it's either a 0 or 1. And I can't remember, I think it's created in the unlock state, so it needs to be first given. Like it hasn't been given yet, right? So an example then, quickly, of how this would happen is that we have, this is just sort of abstraction, and I'll get to why FreeRTOS does this slightly differently. Is that we have, for instance, task A and task B, and we have here a resource. And so this little dot represents the lock that is locking it, this protected resource. Oh, sorry. So this dot is the lock, and then here is our guarded resource. So this is the memory location, for instance, the little box where we have the lock stored in, whatever you want. Essentially, this dot means that they've got the fuzzy ball. This task is allowed to use the resource. And so both of these tasks want to access the resource, and what happens is the task that executes first gets semaphore take, and because these are an atomic instruction, there will be a first task, right? They can't simultaneously access the value because of atomic instructions. And so task A has taken the resource, and it is now allowed to use this guarded resource. Now, when I'm saying guarded resource, all I mean is it's some region of memory. Right? And so if this is a struct, which we saw in the C programming lecture, it could be a very large, complex data data structure in memory. It could be a single integer, it could be an array, it could be anything you want, right? So task A has obtained the resource, and it is now allowed to access, it's obtained the semaphore and is allowed to access the resource. And so what's going to happen is that if task B tries to then take the resource, it's going to fail because task A has it, and so it's not going to be allowed to access the guarded resource. And not until task A has given back the semaphore will it be allowed to then take it and get access, right? And so task B here, when it tries to take it, it's going to enter what is like, for instance here, it's going to enter a block state. And this is what it's saying, if task B opts to enter a block state, meaning that in its semaphore take it put in a block time, so it said, hey, okay, if I don't get it, I want to block, it's going to enter a block state until the resource is available. And so once the resource is available, it's going to take it and it's going to unblock and take the resource, right? And so task B has now taken the resource, which is written here, and it now has access to this guarded resource. And so when it's finished with the guarded resource, it has to give it back. And so we have to be very careful, and this is when it comes up, this is the programmer's responsibility, that you take a lock and you give it back. Because if you don't give it back, you might never unblock again. Other tasks are not going to unblock, and this is when you can run into problems like a deadlock, and a deadlock is a situation when a system essentially freezes because you have created a situation where you can no longer obtain these locks that you forgot to give back, for instance, right? So then I was talking about how FreeRTOS has a slightly different semaphore implementation. And so the difference is that semaphores in FreeRTOS are used for synchronization. And so what is synchronization? And so synchronization is really either passing data, meaning like literally passing a flag or passing a byte, passing a structure, what have you, managing concurrent access, but also specifically in FreeRTOS' sense, it's signaling, meaning it's sort of saying an event has happened or one task triggering another task. And as I was saying in the this sort of scheduler example demo, that determining the order of your task execution you shouldn't rely on the task create order, but you should use, for instance, synchronization methods to guarantee that this task executes and then it tells this task to execute. And by doing this sort of sending synchronization signals, you can guarantee like properly the order of execution. But not exactly here, I'm blocking tasks, so signaling, these two sort of sit together. This one task could signal another one to unblock and continue executing. Timers, and so we'll just go through, for instance, how like task execution, and this is the classic like semaphore FreeRTOS example. When they look at the POSIX definition of a semaphore is this lock that you take and then you give back, right? But FreeRTOS implements it slightly differently in that a semaphore is given by one thread and taken by another. So it has this sort of signaling, like one person is handing the ball to the next person as a signal, but they don't need to give it back, but they're waiting to get given the ball, right? And so a synchronization example is that some event happens, it gives a semaphore while this processing event is trying to take it. And so while it's trying to, it's going to block and wait for it to, and wait until the semaphore is available to be taken. And then we have this sort of this signaling of some events happened, and then this processing is going to happen as a result of this like passing of the semaphore. So the difference is that FreeRTOS, the semaphores are given by one task and taken by another task, right? So this is the key difference. Similarly, we can do the same thing with a counting semaphore, in that you can imagine that we have one sort of task. Like a good example is network packets. Like one task is reading in packets and one task is processing them. So as one task is reading them in, it's incrementing, and it's saying, okay, yep, cool, plus, packets, we have lots to process, and as they're getting processed, it's decrementing it. But one task is giving the number to the other task. So one is incrementing the number and the other one is decrementing the number. So one task is only doing an increment or a decrement, but not actually incrementing and decrementing. And so this is why this is the critical difference, and also why it's really a synchronization method between two things. So it's synchronizing, not so much locking data in memory, right? Because we'll get to where we sort of adapt the semaphore to lock using what's called a mutex, and this is what's then FreeRTOS uses as the locking when I was talking about sort of like this take, modify, give example, right? So semaphores and FreeRTOS are used for synchronization, whereas mutexes are used for what is traditionally known as like shared resource locking, right? So I think we can sort of skip this. So the problem though with this sort of classic semaphore, so like now I'm sort of not talking about the synchronization FreeRTOS semaphore, but this classics, what POSIX defines as a semaphore, this binary atomic increment or decrement of a value in memory, is that you can run into the problem called priority inversion. And so a really easy way, or sort of like the definition here, which I've written, is like a task with a lower priority runs before a high priority task, and it is stuck into a block state, waiting on a lower priority task, and something can happen, which I'll explain using these two pictures. And so we can see here we have three tasks with different priorities. And so the lowest priority task is executing. It takes a resource. So there's little flag is shown as a resource, and then it's doing its thing, and then it's preempted. So at task T2, so the tick, the scheduler is invoked, and the high priority task is saying, hey, I want to run. And so yep, that makes sense. Low priority task should get preempted by a high priority task, so the high priority task starts to execute on the system. So then the high priority task is going to attempt to take the semaphore. But task one, the low priority task still has the resource, it still has the semaphore, so high priority task can't take it, it's going to block, right? If it can't take it, it blocks. And so it's going to then block and surrender control of the CPU, so the low priority task will continue executing. Okay? And this makes sense. Up until this point in time, we're good. This is normal behavior. But the problem is that this low priority task is executing, and then a medium priority task, if it wants to execute, it can preempt the low priority task because its priority is higher. And so we can get this preemption here where a medium priority task is executing on the system, although our focus should be on unblocking or getting rid of this resource so that our high priority task can execute, because we should be focused doing everything we can to get the high priority task to execute. And so that is why at this point in time, with this preemption, we have priority inversion, because we have essentially made this medium priority task, which is executing on the system, more important than this high priority task, which is blocking on a resource. And so then what's going to happen is that this medium priority task is going to run for some unbounded amount of time. It could be forever, and then we're in a really big problem, until it surrenders its control again to the low priority task, because it won't be the high priority task because it's still blocked on the resource. The low priority task will then eventually give up the resource it wanted, which can then mean that the high priority task continue to execute. But our problems already happened in that this medium priority task execute in the middle. So this is the problem, and it's called priority inversion. Now the solution is really quite simple. Same thing happens. So you'll see this first sort of two steps are the exact same thing. Low priority task executes, takes a resource, gets preempted by high priority task, which then executes until it tries to take a resource and it blocks. Now the slight difference is at this T3, or actually it happens here at T1, is that when this resource is taken, the priority of this task, the low priority task, is raised to have a sort of a virtual same priority as the highest priority task that wants to obtain it. So not when it's taking it here, but at the moment that this high priority task attempts to take this resource, this low priority task priority is raised to be the same. Because we want to, by doing this, we're saying, okay, I want to focus on getting this high priority task to run, therefore to ensure, or to make it sort of to focus on releasing the resource I need, I'm going to make the task that holds it the same priority so that everything is happening focused on this high priority task getting to run, right? Therefore, at this point in time, this low priority task has a virtual high priority. Therefore, when the high priority task blocks and surrenders the CPU again to the low priority task, it will continue executing. And at this point in time, like T4, when this middle priority task tried to start up, it won't happen because the low priority task has a virtual high priority. The medium priority can no longer preempt it, and so we won't get this priority inversion or this preemption from the medium priority task. And so the low priority task will continue execution until it releases its resource, at which point in time we will then go back to the higher priority task, which will then be able to obtain it and then sort of give it back, right? And so this is the solution to priority inversion, but this temporary raising of the low priority task's priority to that of a high priority task who's trying to obtain a resource which it owns or holds. So hopefully that wasn't too confusing. But this is the problem. And so this priority inheritance is a solution, and this is implemented using what we call a mutex, which stands for mutual exclusion, right? And so what a mutex is it is essentially a semaphore that has sort of some extra logic that implements this priority inheritance such that we avoid priority inversion, right? And so using FreeRTOS, or like in general, a mutex is exclusively used for locking a resource, for sharing some memory region. So it's not used for synchronization like a semaphore and FreeRTOS, but it's specifically used for shared resource, meaning that is no longer given by one task and taken by another task. It needs to be taken and given by the same task. When the task wants to use a resource, it takes the mutex, it does its thing, and it gives it back, right? And so therefore, the API for FreeRTOS is very similar in that it uses the same X semaphore take and semaphore give. It just, instead of putting in, they both have the same handle type. The only difference is that they use a different create function call, right? So you'll both have a semaphore handle. Then the difference is that you'll use a X semaphore create mutex instead of X semaphore create binary, I think it was. We see here. Let's see if I'm back. Binary, right? Where were we? So Mutex example. In the emulator, which we'll use this in the tutorials, there's a mutex being used to lock essentially the X and Y coordinates of the mouse, because they're stored in a structure in the background libraries. Essentially, there's one copy of the mouse's actual location, but you might have multiple tasks that want to use these values. And so what actually happens is that inside the structure that stores the X and the Y, you have a lock. So the semaphore handle, this is the handle to the semaphore. And here I've just called it lock. And so this is the mutex that needs to be obtained before you use these values and then given back when you're finished with them, right? And so you can see this here, and it's in it. We just use this X semaphore create mutex because in our structure, when we initially create it, this semaphore isn't initialized, so it's not actually ready to be used. And then once we want to actually, in a task, we want to get the value, what we have to do is you can see here, this line of code here, we first take the X semaphore take, we're taking the mouse.lock. This max delay here means, okay, block forever, block until we can obtain the lock. And then once we have the lock, so once it'll stop at this line until we get the lock, and then once we continue, it's actually using the value. As we can see here, we're actually setting it to some value. So we're writing into the memory, we're writing into memory again, and we're finished with the memory, and then we give the lock back, right? And so the way that we can guarantee that we can actually get these values without creating a problem is that we can make copies of them, right? And because if you take a value in memory and copy it somewhere, you can copy it to a value that is only used by each task. So if two tasks want to read the X coordinate, you essentially make two copies of them and give them each a copy. And because the copies will be somewhere else in memory, they won't be accessing the same memory location. But you still, when you're making your copy, you still need to take the lock, which is what's done here. If this is a function called getMouseY, so we're trying to retrieve this value, which is in the structure with the lock. And so what's going to happen is you'll create a copy of the data. And so this is returned from the function, as we know that the stack will return one value. So we'll create the value that we want to return from the function. We'll then take the lock, essentially also delaying forever. So we want to take the lock that's locking the mouse. We'll then set the return, this variable that's returned from the function, to have the value of the Y. And because now we've finished the reading, this line is the only line that actually uses this mouse.y, or the mouse structure. We'll give the lock back, and then we'll return the copy in this ret here. So this is how you can use a lock. And so we'll see this now, if I'll do a quick example showing how mutexes and semaphores are really used in the FreeRTOS API.